Okay, we are in section now 8.8, and we are talking about applications of Taylor polynomials. So you know how to find a Taylor series. So what's a Taylor polynomial? Well, let me show you. Let me show you in the book here. So and I'll just mention we're going to be exploring applications of Taylor polynomials. Okay, how they approximate functions. Okay, and then, well, they also mention below how physicists and engineers use them. We're gonna, and they have some applications, but you know, we're trying to stick to the math concentration here. But it mentions physicists and engineers use these Taylor polynomials. They have it. Hold on here, one moment. They have it highlighted right here that physicists and engineers use Taylor polynomials in such fields as relativity, optics, black body radiation, electric dipoles, and building highways across a desert. Okay, the highway across a desert one, I'm familiar with that application. Maybe if we have time, we can look at that together. It's actually exercise 31 in your textbook in section 8.8. All right, let's continue here. Okay, so let me just remove highlights. So here is the Taylor series. There's the Taylor series where the function is equal to its Taylor series across some interval of convergence. And we are adding an infinite number of terms in this series. So, of course, if we want to approximate a function, we have to take a number of terms in the series, and that's called a Taylor polynomial. Okay, and that's what they have down here. So what you're doing here, maybe I'll highlight it. I kind of don't like things, we just kind of try to highlight this and this. So if you were to take that Taylor series above and take the nth partial sum of the series, which we think of as the first n terms of the series, but you know, I mean, sometimes when n starts at 0, and you know, they add the first 5 terms that they add the first 5 terms of the series, they'll call that the fourth partial sum. Okay, so you just have to kind of watch for that. But let's just for now, the nth partial sum, the sum of the, well, if we look below, the nth partial sum, which is denoted as T sub n, T stands for Taylor polynomial, that's the sum of the first n plus first terms. So a Taylor polynomial T sub n, okay, in that second highlighted box there, is a polynomial of nth degree. Nth degree. So, you know, you remember second degree polynomial, third degree polynomial, fourth degree polynomial, so forth. A Taylor polynomial, T sub n, is a Taylor polynomial of nth degree, and it comes, those terms, the terms that you see here come from, those are the terms of the Taylor series. And of course, if you have a function, and you have its Taylor series, well, and then you look at Taylor polynomials, the more and more terms of the Taylor polynomials you use, the better the polynomial will approximate the function. So, like for example, in this figure 1, we're going to get to now, you know, I have some examples I want to do with you. But in figure 1, what they have here is the function e to the x power. And they've graphed some Maclaurin polynomials. I know they're Maclaurin polynomials because they're centered at x equals 0. But they call them T1, T2, T3. So you have the T1 of x, that's the line. Well, what's in figure 1? What's the degree of a line? In other words, here's what I'm trying to say. Let me say it another way. Let me say it another way here. Hold on here. That's right, Nathan. So T1 of x, in this case, if your function, if your function is equal to e to the x, okay, then that is equivalent to this Maclaurin series, and the interval of convergence goes from negative infinity to infinity. Now that, you can just look at that table in section 8.7, or my handout from section 8.7 in the course content folder, course content in Blackboard, that link, right? Okay, so one moment here. So then starts at n equals 0. So the terms of this are going to be, 1 plus x squared over 2 plus x cubed over 6, and so forth. Okay, so T1 is just 1 plus x. So I'm doing this to help you understand figure 1 from section 8.8. T sub 2 is 1 plus x squared over 2. T sub 3, the third degree Taylor polynomial, would be 1 plus x squared over 2 plus x cubed over 6. So these are your first 3 Taylor polynomials. And you can see all we're doing is just pulling terms from the power series. Just pulling terms from the power series. And in the picture here, what they've done, in fact, in figure 1 is they've graphed e to the x, that function, along with the first 3 Taylor polynomials. Which polynomial does the best job in approximating the exponential function around x equals 0? Well, I should say they all do great at x equals 0, but if you move away from x equals 0, which Taylor polynomial does the best job in approximating e to the x over a longer window? That's right, Renat. It would be the third degree Taylor polynomial, t sub 3. That makes perfect sense because you're taking more terms of the series. So with more information, you can get a better approximation, right? So are there any questions on that? Okay. Well, let's go ahead here now. Given that, let's go ahead and look at an example. Let's see how these Taylor polynomials can be used. I mean, you're learning all this really interesting math. Let's put it in, let's do an application. Okay, let me give you a moment to copy this example down. Okay, so what we want to do is we want to approximate the function given by the cube root of x by a second degree Taylor polynomial about a equals 8. Okay, now let me ask you this. Why are they picking a equals 8 to expand this Taylor, for the expansion for this Taylor polynomial? Why are they choosing that? Why don't they choose like a equals 7? What's so special about a equals 8? In regards
it's a perfect cube root.
That's right. That's right, Maria. It's a perfect cube root. That's good. That's right, Nathan. So we want to expand our Taylor polynomials about kind values of a, because what's going to happen is when we compute the derivatives of the function, they're going to all involve like some type of cube root, you know, and having a equal 8 will make it easier. You know, remember what we have to do here. You know, since this cube root of x, since it's not in the table here, I have to derive the Taylor polynomial, and I have to derive it, using the formula here. Although we're only looking for T2, which is the second degree Taylor polynomial, so we would only be computing the first 3 terms, right? But in those terms, you see, you have derivatives, the function evaluated at a, and then the second term has the first derivative evaluated at a, and then the third term has the second derivative evaluated at a. So to make the computation of those derivatives easy, we need to pick a good, nice value of a. Okay, so a equals 8 is a good value. So now also what we're going to do is once we get this polynomial, we're going to check on its accuracy. Okay, so we're taking a cube root function here, and we're going to say, hey, this cube root function, we can approximate that with a polynomial, and that's going to help us. For instance, if I wanted to find the cube root, say I wanted to find, let me see here. Say I wanted to find like the cube root of 8.24. Well, we don't know how to find that offhand. That 8.24 isn't a nice value. There's no perfect cube root of that. We don't know how to find it, but if we can have a polynomial to help us, we can always evaluate a polynomial without too much difficulty. We could approximate that cube root of 8.24 with the polynomial. But we'd like to know over range of values, x between 7 and 9, how accurate is the approximation? Okay. In other words, cube root of 7, how accurate would that approximation be using the Taylor polynomial? Cube root of 9, how accurate would that approximation be? That sort of thing. Okay, well, we got to build the Taylor polynomial. And again, we're going to build it using our Taylor series formula. So how many derivatives do I need to find for the second degree Taylor polynomial? How many derivatives again do I need to find? 2. That's right, Renat. All right, so here we go. So here's the function, x to the third power. The first derivative is 1/3 times x to the negative 2/3 power. And then the second derivative is negative 2/9 times x to the negative 5/3 power. So for the function and both its derivatives, first and second derivatives, we'll evaluate the function at 8, a equals 8, and the 2 derivatives at a equals 8. And that gets us here. Let me stop for a moment, let you copy. Please let me know if you have any questions. Okay, so now that we know we know what f of 8 is. We know what f of 8 equals 2, f prime of 8 equals a 12th, and f double prime of 8 equals -2 over 188, which, by the way, we could write as -1 over 144, right? So, and you know that WebAssign is going to want simplified radical forms, so we're going to leave the fractions as they are, and now we're going to go forth and construct the polynomial. So I constructed it here. T sub 2, the second degree Taylor polynomial, will equal, in the end, it will equal 2 plus 1/12 times x minus 8 minus 1 over 288 times x minus 8 squared. Please let me know if you have any questions. I'm going to just give you a moment to copy that.
So I have a question. I was unsure when you asked about how many terms we're going to need. So how did you figure that out?
In this problem, it says approximate the function by a second degree Taylor polynomial. So they're telling you, like, the degree of your polynomial is 2, second degree Taylor polynomial. So it's a polynomial of second degree, degree 2. So that means we need to find the first 3 terms. If they wanted a third degree Taylor polynomial, we'd have to go out to the next term where we'd have the cube in there.
Okay, thank you.
So whatever the degree is, that's how many derivatives you need to find.
That's correct. That's right, Maria. That's right. And I'll comment, class, like, okay, so like, you have x minus 8 quantity squared here. But if you work that out, that would be, x squared minus 16x plus 64. And there's your second degree right there. There's the x squared, There's the x squared. Okay. Let me know if you have any other questions. At this point, we could use you know, like let's say you wanted to check your answer to see if your answer is reasonable. Okay, in the homework or on the final exam, you know, you say, you know, you get this answer, and you want to check to see if the answer is reasonable. Okay, well, let's go to Desmos and see if this is a reasonable answer, this Taylor polynomial. So let me see here. One moment. I'll bring up Desmos. Okay, and I've already actually worked on it a little bit here, but let me start fresh. So I'm in Desmos, and I want to do, what was it, the cube root of x. So the cube root of x is x raised to the 1/3 power. There's the cube root of x. And now let me do my second degree Taylor polynomial. Let me plot that along. Oh, well, now, okay, hold on. I'm gonna do something here. Let me plot that. So we got what is it? 2 plus 1/12. Let me just see if I can. 2 plus 1/12 times x minus 8. Okay. Plus, or minus, I should say, minus 1/288 times x minus 8 squared. Okay, and there's the picture. How's the polynomial do?
Well, you're only looking between 7 and 9, right?
Good. That's right, Maria.
So it's almost exact.
So this window is not a very good window because our Taylor polynomial is about a equals 8. That's where we're centering the polynomial. So we're not expecting it to do a good job like near x equals 0 or x equals -2, but it's supposed to do a very good job near a equals 8. So what I'm going to do is I'm going to go up here to my little wrench here, and I'm going to change my axis here a little bit. I'm going to maybe go from 0 to I tend to like to include the origin traditionally in my graphs, but I'll go from 0 to 12. And then the y-axis, I'll go from, say, 0 to maybe, I don't know, 2.5. Hold on here. Okay. Now hold on here. One moment. Let me go back to my wrench. The y-axis, let me go down like from -0.5 to, I like having, you know, my x-axis show, so I got to have some, you know, just go down a little bit there. So, wow, I think I can increase my window even more. Let me see here. We went from 0 to 12. Why don't we go from like 0, let's go from 0 to 20. Hold on, nope, I got to do a little more than that. Then the y-axis, I'll make that like 3. Okay, so let's see. Well, so around a equals 8, Nathan, they do. In fact, the second degree Taylor polynomial and the function, the cube root of x, do intersect at a equals 8 or x equals 8. They do. They agree perfectly there. Okay. But you see, as you move away from a equals 8, how the polynomial, which is the blue graph, it does good for a while, but when does it kind of start to fail? Can you visually? I mean, this is just a visual thing, but if you go to the right, a equals 8, go to the right of x equals 8. When does it start? Can you visually see that, hey, you know, the quadratic here is not approximating the cube root of x?
About 11.
Maybe about, yeah, I was thinking more like 13, but sure, I hear what you're, if you zoom it in, I think you're right on that, Maria. I mean, you can start seeing the difference at 11, and then certainly like at 13, you can definitely see it. And as Nathan says, and then so if x is greater than 13 and x is say less than 5, you start seeing, you know, it not do a good job, not as good a job. So how would you get an approximating polynomial that would do a better job? What would you have to do to get a better polynomial? That's right, Nathan. You'd have to use more terms. You'd have to use more terms. Okay, and it will work. I did a polynomial one time that had, I think it was 9 or 10 terms in it. And, you know, it did pretty good there for a while, you know. All right, well, are there any questions on this? So this is something you could do, you know, when it doesn't take long to do, and it provides a check on your answer, you know, before you hit submit, right? So, okay, great. So let me go ahead here and back to the example here. So we've basically graphically verified that our answer is looks pretty good, and so okay, we can say then that the cube root of x can be approximated by this second degree Taylor polynomial. Okay, it's an approximation, but the approximation gets worse and worse as you move away from a equals 8. The question is, what are you willing to accept? How much error are you willing to accept between your approximation and the true value of the function? And this is where Taylor's inequality comes into play. So let me go back here to Taylor's inequality in the handout. So it's in the book. Actually, Taylor's equality in the book is actually they introduce it actually in section 8.7. They introduce it in section 8.7. It's there a little bit. Well, before example 2, it's there, and they actually prove the inequality. I've written it out here again for you. So here's how the inequality works. We let our nth degree Taylor polynomial be centered at A, and if the next derivative, the n plus first derivative, is less than or equal to m for a certain set of x values, saying that x, the absolute value of x minus a, is less than d, is equivalent. That's equivalent to saying that x minus a is less than d and greater than negative d. Hold on, let me do this again. This just means x minus a, and a is given to you normally, or a is not always given to you, but you usually know based on the problem what a should be. Okay, and I'll show you that later on. So x minus a is greater than negative d, less than or equal to d. So that means if we add a to here, and to here, and to here, then, you know, this cancels. So x is less than or equal to a plus d and greater than or equal to a minus d. So what they're saying is, if you have, your value of a, then you're looking around some neighborhood of a, So if the absolute value of the n plus first derivative is less than or equal to some value m over this range of x values, okay, then the remainder, or the error in your approximation, which is the difference of the value of the function and the Taylor polynomial, that'll satisfy this inequality. And this is known as Taylor's inequality. Okay. Now, the x minus a less than or equal to d, for our problem, it's x is less than or equal to 9, greater than or equal to 7. And that's like saying, x is less than or equal to, let's say this the right way. Like in our problem that we're doing, we have, when they say that x is between 9 and 7, of course a is right in the center of that. If you were to write the absolute value of x minus 1 is, no, if you write the absolute value of x minus 8 is less than or equal to 1, that means that x minus 8 is less than or equal to 1 and greater than or equal to -1. And so x would be less than or equal to 9, add 8, everywhere, and greater than or equal to 7, right? I'm sorry. I want to show the whole thing. Hold on. Let me do it again here. So I'm focused here. So for our problem, okay, if you have the absolute value of x minus 8 less than or equal to 1, and 8, by the way, is your a value, right? Then x minus 8 is less than or equal to 1 and greater than or equal to -1. But if we add 8, on everywhere here, we know how to manipulate inequalities. If you do that, you're going to get then that x is less than or equal to 9 and greater than or equal to 7, right? So when they say that, x is between 7 and 9, that's a fancy way of saying, well, that's a nice way of saying the absolute value of x minus 8 is less than or equal to 1. I just wanted you to, help tie things in for you here. Okay, let's continue then. Are there any questions on that? All right, let's continue on. This is in the recording, of course. So here's the question. How accurate is the approximation for values of x between 7 and 9? So let's say I want to approximate, the cube root of 7.3 or the cube root of 8.6. Okay, we don't know what those are. But let's say I wanted to use this Taylor polynomial to approximate those values. Well, all I would need to do, right, is substitute in for x, like for the cube root of 7.3, I'd substitute in 7.3 where the x goes. And I would evaluate this. And that can be evaluated without high-level math. It's just ultimately addition, subtraction, multiplication, and division, okay, which mathematicians 300-400 years ago could do without computers, right? All right, so, but computers, of course, do those. Those are called flops, right? Arithmetic flops. So How accurate is the approximation, our approximation, when x is between 7 and 9? How accurate is this second degree Taylor polynomial? Well, what we're going to do is, here's the inequality. Now, the remainder, the error, well, r sub 2 is equal to the difference between the second degree Taylor polynomial and the cube root of x. So by Taylor's inequality, how big is that error? How big would that error be? You know, which will tell us how well our polynomial approximates the cube root of x. That, according to Taylor's inequality, is less than or equal to m over 3 factorial. Okay, because 3 factorial is that's where you have the n plus 1 factorial in Taylor's inequality. And, you know, n is equal to 2. And then you have x minus 8. Well, 8 is a. And then to the n plus first power, that's 2 plus 1. So the only thing we need to do here is we need to figure out what m is. We need to figure out what m is. Okay. It's similar. Remember in section 5.9 when you did approximate integration and you had the error bounds for the trapezoid and midpoint rules, and you had to determine what k was, and k was based on the absolute value of a like, you know, for instance, a second derivative. How many recall that? Finding the value of k for numerical approximation, error bounds for trapezoidal and midpoint rules. That's back a ways, but how many recall that? Okay, Michelle remembers that. Renaud remembers that. So it's the same, I mean, a little different, but same principle. Same principle. So what am I going to do here? All right, I'm gonna have to find the third derivative of this function, the cube root of x. So I do that. And incidentally, not hard to do. Not hard to do, because we knew in order to get the second degree Taylor polynomial, we needed to find the second derivative, right? And the second derivative, if you recall, was equal to negative 2/9 times x to the negative 5/3 power. Right? Let me write that again. I like my stuff to look good. Right? So, okay, what's the third derivative is just the derivative of the second derivative here. And that will get you 10/27 times x to the negative 8/3 power. Now, what do we want to do? We want to look at the absolute value of that third derivative when x is between 7 and 9. But you'll notice that when x is between 7 and 9, the absolute value of the third derivative is just itself. You know, you can drop the absolute value because this here, this is greater. 10/27 times x to the negative 8/3 is greater when x is between 7 and 9. And what I do is I write this third derivative as 10/27 times 1 over x to the 8/3 power. Now, why do I do that? Why do I take x to the negative 8/3 power and write it as 1 over x to the 8/3 power? Why do I do that? I do that because it helps me see that, hey, this third derivative is decreasing with x. Clearly, because x to the 8/3 is in the denominator of this rational function, as x gets larger, the third derivative function is going to decrease with x. It's going to decrease with x. And this is going to help us then determine what m is. So what we have to do, right, for m is, and we're going to show this on the next page, but m is going to equal 10/27 times, hold on here. Let me put it over here. So m is going to equal 10/27 times 1 over x to the 8/3 power, but we have to put something in for x. Now our choices for x are, x can be anything, any number between 7 and 9, including 7 and 9. If we're going to be conservative, we would want the biggest error bound possible, right? Because we don't want to say our approximation's more accurate than it is. So we want to pick, over when x is between 7 and 9, we want to pick a value of x, the value of x that makes m here the biggest value. So what am I going to put in here? What number is going to go there? Okay, Nathan's saying 7. Renaud's saying 7. Okay, hold that thought. I'm going to go ahead and put the 7 there, okay? I'm going to go ahead and put the 7 there. That is correct. Hold on. Okay, I'm going to put a 7 here. Why 7? Why pick x equals 7? Why not pick x equals 9? M would be smaller. And why would it be smaller? Why would m be smaller with x equals 9, Renaud? Good. So what Renaud's saying is this, our third derivative decreases with x. It decreases with x. So so that means, if your third derivative decreases with x, I mean, if your third derivative, this is some rational function, decreases with x, right? And you have a 7 and you have a 9 here. The third derivative evaluated at 7 would give you the biggest value. And so that's what you're going to use. So this is your value of m right here. And you notice I don't use a decimal approximation yet. Okay.
So,
all right, are there any, yes, Nathan.
So the m value, you're always going to use the derivative higher than the degree of the Taylor polynomial that's asked for?
That is correct. That's correct.
Okay, thanks.
All right, you're welcome. All right, are there any other good questions? Okay. Well, if we're good then, let's go ahead and move on to the next page. So here we know our value of m, and now, so m would be greater than or equal to, well, this, hold on. This is actually not what we want here. This isn't, no, forget that. That's not, don't even look at that. Don't even look at that. We're just going to take m equal to 10/27 times 7 to the negative 8/3 power. Let me just see what I wrote there. Let me just see. Yeah, that's fine. That's fine. We've established why that's true. We've established that. Let me just erase this here from my notes. Always refinements. So now what we're going to do is we're going to substitute that value of n in the bound here for Taylor's inequality. Okay, there it is, right there. But don't forget, we also have that absolute value of x minus 8, right? We have that too. We're raising that to the 3rd power. So we want the maximum value for that as well. We want the maximum value for that as well. And when x is between 7 and 9, the largest absolute value of x minus 8 would be 1. So the bound on your error of your approximation would be 10/27 times 7 to the negative 8/3 power over 3 factorial times 1 cubed. And that will equal 0.0021 over 6, which is 0.00035. Are there any questions on that up to here? Okay, well, so long as x is between 7 and 9, our 2nd degree Taylor polynomial approximation of the cube root of x is accurate to within 0.00035. Or, let me see, 3,500 thousandths. It's within 3,500 thousandths. And I have I copied a couple figures here, so it could be in the recording. This we did in Desmos, really. We drew the cube root of x in T2. And then this 2nd figure here, figure 3, just shows the remainder, the actual difference between the 2nd degree Taylor polynomial and the cube root of x. It shows the error, absolute value of the error. And you can see, you know, around, I mean, of course, when a equals, hold on here. Yeah, so the axis got to be a little careful. The horizontal axis goes from 7 to 9. So right here in the center is a equals 8. And that's where the polynomial approximates the cube root of x perfectly at the center point at a equals 8. But then it gets worse as you move out, and so the error gets worse. That's what this picture is showing. And then here 8 is right about here. So this is the x-axis here. Okay, and let me ask you this. Let me ask you this regarding this absolute value of x minus 8 right here. Suppose that x, instead of being between 7 and 9, suppose that x were between 7 and 9.3. Hold on. This is just an aside here. Hold on, I get my little eraser. Learn how to use this better now. Okay, so let's say, let's suppose x were between 7 and 9.3 instead of 7 to 9. Then what would what would you have for like the absolute value of x minus 8? Hold on. Sometimes a mouse is easier to work with. Come on now. What I'm trying to say is, for the value of x here, I'm going to put a 9. Going to be a 9.3. Good, Nathan. Good. Good. So let me just do it again here. I just need to have room. I can't have, I just, So again, we're supposing that x is between 9.3 and 7. And we're wondering, for this part here, in the Taylor's inequality, which is absolute value of x minus 8, what would its largest value be? We want to maximize that too, right? Well, it would be 9.3 minus 8. So you have to look at your interval, right, to determine what value of x you're going to put in there. And that value of x that you put in here, in this case it was 9.3, it is independent of your m value. Independent of your m value. Okay, it's like a separate criterion. All right, are there any questions before we move on? Okay, well, who would like to test out the approximation? Who would like to test out the approximation? It's kind of like, we bake this cake and we want to taste our cake. All right, Nathan knows what I'm talking about. All right, well, here we go. I'm going to try to estimate the cube root of 8.24, and I'm going to pretend, I'm a computer, or I can add, subtract, multiply, divide. I can do flops, or I'm a mathematician from 300 years ago. Okay, it's always easy to add, subtract, multiply, and divide, right? So here's what we do. Let's try our approximation to estimate the cube root of 8.24. Okay. The cube root of 8.24, 8.24 now is your 8.24 is your value of x. Right? That's your value of x. So we're going to evaluate the Taylor polynomial when x is 8.24. And so I substitute it in where the x goes, right? The a is just my, that's just my 8. 8 is the a. And okay, so let's look at this. I'm trying to approximate the cube root of 8.24. So, okay, well, it's easy to subtract 8.24 minus 8. That's just that's 0.24. Okay, easy. And 8.2. Okay, so this is easy. And 0.24 squared. It's easy to multiply 0.24 times 0.24. I actually did it here. How many remember their basic math? When you multiply two decimals, you move the decimal, you have to move the decimal on the like in the product. Like if the decimal place is 2 decimals over here on 0.24 and 2 decimal places over here on 0.24, when you multiply it, you move the decimal over in the product 4 decimal places. How many recall that from elementary school? Okay, so no problem. We're able to do that. I get 0.0576. Okay, so far so good. Now 12 into 0.24. Okay, let me go back here. Yeah, 12 into 0.24. I bring the decimal point up here. There it is, and it goes in twice. So 0.02. How many remember doing division like this in elementary school? Decimal divided by a whole number. How many recall that? Oh my goodness, you must have done that in school. All right, thank you, Renaud. Renaud's done that. So, okay, no problem. So, all right, I get 0.02, and then I can do 1 divided by 288 and get 0.0002. And then I can add these three together and I get 2.098. So if I'm like, if, I always think of the movie Castaway with Tom Hanks. I don't know if any of you remember that movie. He's on the desert island and he's trying to free himself, and trying to get off the desert island. What's a desert island? Wait, it wasn't. Yeah, it was an island in the ocean, right? And well, so if you're ever in that situation, you could really do some good calculations, right? Well, how good is this approximation? Well, the TI-84, if you type the cube root of 8.24 in there, in other words, that would be taking, try it now. You'll get, if you do 8.24 and raise it to the 1/3 power, you'll get this. Who's trying that? Maybe in decimals are here and is getting this answer. 2.019803268. Okay, Renaud got that. Well, okay, using our second degree Taylor and on the TI-83, excellent. Using our second degree Taylor polynomial, we have agreement to 4 decimal places here, right? 0.0198, right? 2.0198. We have agreement out to the 10,000th place. So that's pretty good. That's not bad. And again, all of the computations, I did this like by hand, you know, I did it all by hand. Okay. Just to, you know, show you that, hey, you know, this is the beauty of these polynomials, these Taylor polynomials. They allow you to do computations. I mean, when you, like, your calculator has algorithms built into it, and you know, their answer probably involves a, I mean, it would involve a, maybe a Taylor polynomial with, you know, more terms, maybe 10 terms. Okay. But how many think that's absolutely fascinating? How many think that's absolutely fascinating? Okay, Maria likes nod, Jacob, Baraka, excellent, excellent. Absolutely, absolutely. Okay. Well, let's do another application here. Let's do another application. Okay, very applicable to computer science, right? What you're seeing here. Okay, so is everybody ready to go to the next example? Give me a thumbs up. All right, Maria's good, and Nicole. Looks like everybody. Okay, let me get there. So one moment. One moment. Okay, let me give you a moment to copy this example down. Okay, so in this problem, we want to use a fourth degree Taylor polynomial to estimate the cosine of 69 degrees. And then we're going to ask how accurate is our estimate. Okay, now there are some angles that we can find the cosine for, like exactly. What are like some friendly, what are some friendly angles? Okay, so to speak. Okay, Nathan says 90, all right. So friendly angles, Michelle says 30, okay, let me list them here, 30. So we got 30 degrees, 90 degrees, that's right, Maria, 60 degrees, 180 degrees, Good, Renat, and Maria says 45 degrees. Okay. What about 120 degrees? Is that friendly? That's right, Nicole. That's friendly, right? You know, you just go out here and your reference angle is 60 degrees. So you remember your trigonometry. Okay, so, you know, 150 degrees. So there's a lot of friendly angles. Okay. Now, of course, for the using them in a Taylor series, we need to use radian measure. Okay, so radian measure is very important and it's used a lot. I heard a comment that I heard one time a comment made that the degrees are used a lot. Well, degrees are used to interpret things, but in terms of computation, you know, you have to convert your angles, this is over 6 here, into radians, right? You have to convert your angles into radians, and you know that. 120 degrees is what? That's 2 pi over 3, and so forth. So, well, I have the cosine of 69 degrees here. I want to estimate that. I got to figure out what A I'm going to use here. What friendly angle am I going to use? What friendly number or radian measure am I going to use here? Well, let's take a look. All right, so Renat and Maria have suggested two possibilities. Okay, so you could use pi over 3, okay, which is 60 degrees, right? That's one possibility. You could also consider pi over 2, which is 90 degrees. Okay, hang on here. Hang on. Okay, so you have two possibilities. Maria, we can only use one of the angles. We can only use one. At least in this class, let's put it that way. Yeah, I know there's like formulas for adding angles and getting things. But good question. Is there another angle maybe that could be used? Another friendly angle? "45 degrees. Okay, good, good. So, okay, you've all given me 3 choices here. Here's choice 1. Hold on. One moment. Pi over 4 is 45 degrees. All right, so choice 1 is 45 degrees. Choice 2 is 60 degrees. Choice 3 is 90 degrees. Now, we could use any one of those values for A. But which one is the winner? Which one's the best to use? That's going to give us the best approximation. That's right, Maria, 60 degrees, because it is closest to 69 degrees. So we want to use our friendly angles. We want to use the friendly angle that's the closest to the ugly angle that we're working with, and that's going to be 60 degrees. So in like WebAssign, they don't tell you for this kind of problem what value of A to use. So this is the thought process that you have to use. Okay. All right. Now, what I'm going to do, are there any questions on this? Okay, so if I look at my table, the table gives me Maclaurin series. And there is a Maclaurin series for the sine of x. There is one for the sine of x. Okay, but Maclaurin series assumes that a equals 0. We are doing a Taylor series about a equals pi over 3, 60 degrees. So I'm going to have to go ahead here and derive my, Taylor polynomial. And of course, I will utilize the Taylor series formula. So that means how many derivatives am I going to need to find for a fourth degree Taylor polynomial? 4. That's right. That's right, Renaud. That's right, Maria. Very good. So here we go. Here we go. Okay, so here's the work. And I do indeed compute up to the fourth derivative. And then for all the function and all its derivatives up to the fourth derivative, I evaluate at pi over 3. And based on that, I can get my Taylor polynomial for the cosine of x about a equals pi over 3. I'm going to just give you a moment to copy all this down. Please let me know if you have questions, okay?
I have a question for you, Professor.
Yes, Nathan.
How do we know? Oh, I guess we know that the Maclaurin series table is not centered around 0 because it's a Maclaurin series, right?
That's correct. This is not a Maclaurin series, it's a Taylor series because it's centered around a non-zero a value of pi over 3.
Okay.
That's right. And actually, too, what I can do here, hold on here. Let's see, oh, that's the wrong. Let me find my stylus. Where'd it go? Here it is. So, of course, this is f of pi over 3. F prime of pi over 3. F double prime of pi over 3. I'm just writing that in to just sort of you can see the help. It'll help you, just be comfortable with the formula. So now that would take a little while to type in Desmos, but probably well worth the while. Okay, now, so what I want to do is I want to evaluate. Now, you don't have to write this, actually. You should probably write this, but I want to evaluate the cosine of 69 degrees, right? So in this Taylor polynomial approximation, you know, I mean, x, am I going to put in, well, can I put in 69 degrees for x? Like, if I do the cosine of 69 degrees, I'd be putting 69 degrees in for x everywhere. But can I do that? Why not? Renaud says no right away. Why not? What's wrong with that? Can't put in 69 degrees. Why not? Very good, Maria. Very good, Renaud. You're in radians. You're in radians. So if I'm going to find the cosine of 69 degrees, okay, I have to figure out what 69 degrees in radians. So what is 69 degrees in radians? Well, you know, Renaud, you're right on that. You're right on that, and I'll show you on the next page. May I go to the next page? Are we good? Give me a thumbs up if you're good. Okay, wonderful, wonderful. Okay, so all right. Here I wrote the formula again, or I wrote the Taylor polynomial approximation. And 69 degrees, to convert it to radians, you multiply by pi over 180 degrees. How many remember doing this in trigonometry, converting degrees to radians using this this idea? Okay, good, good. Abhidar and Maria and Renaud. Okay, wonderful. And now it's back. You're wondering, man, when am I ever going to do this? When am I ever going to need to do this? Hey, here you go. Here you go. You know, it's really nice when things you've learned in the past uh, 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 come up in new things, right? It justifies why it was important. So 69 degrees, it turns out, is, as Renaud said, 69 pi over 180 radians, but that's just 23 pi over 60. And so that's what I'm going to be substituting in for x, 23 pi over 60. And then that goes everywhere where the x goes. I put in 23 pi over 60. But 23 pi over 60 minus pi over 3, well, pi over 3 is equal to 20 pi over 60, right? So all those differences in the parentheses turns out will equal 3 pi over 6 or pi over 20. And you have to do this. You have to do this. You cannot do like a decimal approximation on this step. Okay, you have to have the pi over 20 in there. And then when you evaluate this, you have to type it all out on your calculator. Okay. So what I'll do, let's go to Desmos and work this out.
Can you wait
Okay.
for just a moment?
Sure, sure. Are there any questions?
Thank you.
You're welcome. How's everybody else? Are we good? Marcus is good. Give me a thumbs up when you're ready to. So apparently we should be getting an answer of 0.3583686. Okay, well, let's check it out in Desmos then. So you go to Desmos also on your computers, okay, and go ahead and start typing in this here. Do not take pi over 20 and make it a decimal. Type this entire thing in as you see it, this entire expression in. And I'll do it too. I'm actually going to do it too. I'll do it kind of, I mean, you know, you're doing it, I'm doing it. And I'm just going to do it here. Pi is for pi, by the way. Okay, let me go into Desmos here. Okay, give me a thumbs up if you're seeing Desmos. Good, good. All right, so there you can see I've started, you know, started typing the expression, and you know, I'll arrow over here, and you know, yep, it works. It works. And that's the kind of thing that you know, that you should do. Now, if you try on your calculator, I'm just gonna, well, no. I'm just curious what the TI 8384 calculator says. I mean, you could actually write in Desmos. I'm trying to think. To be honest, well, let me just do it on the calculator here. Mine will say error. You got an error, Nathan? Well, you just have to. Oh no, well, have your calculator in degree mode. Yeah. If your calculator is in degree mode, the thing is, I always hate putting my calculator in degree mode because then I got to remember to put it back in radian mode. How many have had that issue where you put it in degree mode and then you take a test or something, you get the wrong answers because it's not in radian mode? Okay, Maria knows what I'm talking about. So, and Michelle knows. Okay. Yeah, so that's pretty darn good. TI 8384 calculator, cosine is 69 degrees. I get 0.35836, 79495. So pretty darn good, pretty darn good. Any questions? Okay, so this is actually a very accurate estimate of the cosine of 69 degrees. Our 4th degree Taylor polynomial. We used 2 more terms, you know, than the last example we did. Gave us a pretty good approximation. Now, of course, we have to ask the question, what's that mean? Pretty good. You know, we need to quantify what that means. Okay, we need to quantify that, right? So, hold on here. Yeah, how accurate, you know, how accurate is that estimate? So that means it's time to use Taylor's inequality. Taylor's inequality. Okay, and so let's go use it. So how accurate is our approximation? The 4th degree Taylor polynomial evaluated at 23 pi over 60. Well, by Taylor's inequality, you know that this is the structure of Taylor's inequality. The bound on the error is less than or equal to m over 5 factorial times the x minus pi over 3 to the 5th power, absolute value, of course. And it turns out that, well, the 4th derivative of the hold on. Okay, so now the 4th derivative of the cosine of x is the cosine of x. And so the 5th derivative would just be the derivative of the cosine, which is negative sine. And remember, when you have, how many recall, like when you're taking, when you have like a negative, when you have a sine or cosine or negative sine or negative cosine, remember back in section 5.9, you let k equals 1. How many recall that? You know, sines and cosines, they're always between 1 and negative 1. How many recall that? Yeah, Jacob remembers that. So we're just going to make it easy. We're just going to let n equals 1. Okay, now other times if we have like a derivative or whatever, an nth derivative or n plus first derivative, I should say, and you know it's like some kind of exponential function or something, we have to assess if that derivative is increasing or decreasing, and based on that, that's going to determine what value of x we put in the derivative to determine m. But in this case, we'll just let m equals 1. And so m equals 1, there it is. 5 factorial is 120 right here. And the x is 23 pi over 60, right? I mean, we are evaluating the error now at a specific value of x. A specific value of x, right? That value of x is 23 pi over 60. So there's no interval. There's no interval. Okay. And so when you work this out, and again, I wait till the very end to do my computation, we're going to get point, hold on one moment. Yeah, we're going to get point 0.000000797. And that is less than 5 over 10 to the 6th power. So our estimate is correct to 5 decimal places. 5 decimal places. And actually, that is, if you compare our estimate to what you get on the TI-83 calculator, there is agreement in 5 decimal places. Absolutely amazing. Absolutely amazing. So the question is this is accurate to 5 decimal places good enough for you? Like if, for instance, if this is if this is something being used for like astronomy. Okay, 1, 2, 3, 4. Hold on. Let me do this again. 5 decimal places. 1, 2, 3, 4, 5. Yeah. Would this be good enough for astronomy calculations? You know, in astronomy calculations, if you're off just a little bit, the star is very far away, right? That can make a big difference, right? So, you know, you might want to be accurate to 20 decimal places. Well, for 20 decimal places, you would have to take more terms of the series, right? You'd have to have your polynomial. Maybe for 20 decimal places, you might need a 30 or 40th degree Taylor polynomial. And that's where computing power gets involved, right? That's where computing power gets involved. How many think this is absolutely, really absolutely fascinating, what you're learning here? Michelle's loving it. Nathan likes it. Leping likes it. And Jacob, Nicole. Yeah, you're seeing how this is used. You know, you're seeing how this is used. Now, what I want to do is I want to look at one example from the book. It should only take about maybe 5 minutes to look at, and then I think I can give you some time here to work on section 8.8, but I don't want to move till everybody's ready. Okay, so just give me a thumbs up when you're ready, and then we'll move to the book. Okay, Leping's ready, and Let me ask you this. Let me ask you this. Nathan, we want M as large as possible. We want M as large as possible. Because when M is as large as possible, it makes the bound on our error larger, which we want to do because we don't want to say that our approximating polynomial is more accurate than it is. Let's see. Marcus says, why is it correct to 6 decimal places rather than, let's say, 6 or 7? Well, 5 over 10 to the 6th power, if we take 5 over 10 to the 6th power, hold on, that's going to equal 0, let me get the stylus out. It's going to equal 0.000, hold on here, 0.005, right? This is like, one moment. Yeah, 5 zeros here. So if you had like, and certainly this value is less than that. Now, if you had like, say 5 over 10 to the 7th power, that would be 0.12345 6 zeros with the 5. Oh, see? Now look at this, Marcus, look at this. Is 0.000000797 smaller than 5 over 10 to the 7th here? No. So you see, you can't say that your approximation is accurate to 6 decimal places. It's accurate to 5 decimal places. And if you type in on your TI-83 or 84 calculator, or maybe Desmos can do it, but if, I mean, I assume it can, you know, you can get it in degree mode and do it. I'll let you investigate that. But like on the TI-83, 84 calculator, if you type in 69 degrees to take the cosine, you will have agreement within 5 decimal places. Renaud, you confirm that as well, right? I think Renaud, you confirmed that. I confirmed it. Okay, all right. So Marcus, does that make that's why I said 5 over 10 to the 6th power. That's the best I could do. Okay, that's the best I could do. Okay, very good, very good. I'm going to make one more comment here. One more comment. This here, well, could have I used? Well, no. Let's. Well, no. Okay. So let me just make a comment here. So you know how like when we have a series of terms, I want to be a little careful how I say this. Let me look at the series here. So here's the polynomial. Here's the polynomial. No. All right. No. Let's just go right to the book. I'm happy with what we did here. I want to go right to the book and show you something here. So sometimes, like here in example 2, okay, they say, what is the maximum error? What is the maximum error possible in using this approximation for the sine of x. And then they say, okay, well, let's just focus on the first part. Okay, this is the part when x is between negative 0.3 and 0.3. Okay, on the second part, when it says you find the sine of 12 degrees, correct to 6 decimal places, you know how to do that. You know how to do that. Well, actually, one moment. Let me look at that a little bit closer. One moment. This is example 2, section 8.8. Yeah, I really just want to focus on this part. So notice here's the Maclaurin series. What kind of series is this? What do the terms do? Plus, minus, plus, minus, plus, and so forth. What do those terms do?
Alternate.
They alternate. And when you see an alternating series, that you can think of the alternating series estimation theorem. So you know, we have the Taylor's inequality that can get a bound on our error, but also if we have an alternating series, if our function can be written as a alternating series, we can employ the alternating series estimation theorem. Okay, so in this case, okay, if we were to just use the first 3 terms of this Maclaurin series, okay, if we were to use, no, can't do that. I'm going to highlight. I'm going to just try to highlight it. Hold on. There we go. Put in pink here, and then there's the series above. So if we were to use the first 3 terms of this Maclaurin series to approximate the sine of x, then the error in approximating the sine of x with that Maclaurin series would be at most the absolute value of x to the 7th over 7 factorial. Because that's what the alternating series estimation theorem says, right? You can the error between the sine of x and this 2nd degree, or I should say it would be the 5th degree Taylor polynomial, or Maclaurin polynomial, because x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, that's a 3rd degree Maclaurin polynomial. The difference, the error in that approximation would be at most the 4th term, absolute value of x to the 7th over 5,040. So this is something you've dealt with before. How many recall doing this like on the exam, this kind of thing? I mean, you didn't do it with power series, but you had it with series with like values. How many recall that? Okay, Renaud recalls it, and the number of you do. So in this situation, okay, if x is between negative 0.3 and 0.3, then the error would be smaller than 0.3 to the 7th power over 5,040, which is approximately 4.3 times 10 to the negative 8th power. So I just wanted to show you that we can employ the alternating series estimation theorem as well to help us get a bound on our error. But that only works if our Maclaurin series for our function is an alternating series. Okay, are there any questions on that? That's really, I just want to talk about that. You'll have a few problems in section 8.8 towards the end that deal with that. Are there any questions? Okay, I'll stop the recording.